I am Professor N.B. Hulle from G.H. Raisoni Institute of Engineering and Technology, and in this video we will calculate the current in 10 ohm resistance, which is here load resistance of 10 ohm using the Norton's theorem. Now we will apply the steps for the Norton's theorem. As I discussed in the previous video, the first step is removing of the load resistance and shorting the output terminals. Here, if we are removing the load resistance and if we are shorting the output terminals, the figure for the first step is like this. Here, we are not doing anything extra, just we are applying the first step, that is removing the load resistance. Here, we have removed the load resistance and this load resistance is replaced by the short circuit. This is the short circuit. Here, this ohm is 2 ohm, it is 5 ohm, 6 ohm, its voltage is 2 volt, this voltage is 2 ohm, it is 1 ohm, and here it is 40 volt. Now, our aim is to calculate current in the load resistance. I will name this current as a IN, that is Norton's current. And in the step number 2, we will calculate current in the short circuit, which is the Norton's current. As I discussed previously in the explanation part also in the previous video, I used the nodal analysis method for the calculation of the current in the short circuit in the previous video just. Now here in this video, I will use the direct inspection method for the calculation of the current. I will name this current as I1 and here this current as IN, which is Norton's current. Two currents, here it is IN. Now, how is the direct inspection method? I will brief here about the impedance matrix or resistance matrix R11, R12, R21 and it is R22. R22. Now here, if I am preparing this matrix, this R11 is the resistance of the first loop, which is 6 plus 1, 7, 7 plus 2, that is 9. Here it is 9. Then R22 is the resistance of the second loop. This is the resistance of the second loop. That is 6 plus 2, 8. 8 plus 5, 13. This is 13. Diagonal elements are positive, remaining all elements are negative. Means R12 and R21, this is the resistance which is common for the first and second loop and second and first loop, which is minus 6. This is minus 6. Here it is minus 6. The unknowns are I1 and IN, which is equal to the constants C1 and C2. Here, the constant C1 for the first case, if we are traveling with the direction of the current, we are able to calculate the constant. If we are traveling with the direction of the current, negative to positive, that is a plus 40. Then here, positive to negative for other source, which is minus 2, that is equal to 38. 38 is the first constant. What is the second constant? If we are traveling with the direction of the current here, we are traveling from negative to positive, which is plus 2, then there is no source, which is equal to 2. This here, this is the constant 2. And if we have this matrix, we can calculate current by using calculator directly. And here, we are interested in the calculation of the Norton's current, which is IN, that is second current, second current IN. If I am using the mode of the calculator and if I am going for 1, which is equation, then number of the unknowns are here. I am using the number of unknowns are the 2. Then we will enter the value of A1, which is 9. Then value of the A2, which is minus 6. value of the C1 which is 38, then value of the A2 which is minus 6, then value of the B2 which is 30, value of the constant 2 which is 2. Here we will get the first value which is I1 6.24 and second is 3.03. This here IN is 3.03 amperes. That is nothing but the Norton's current in the short circuit. If we know the Norton's current, that is step number 2, we will use the step number 3. And in third step, we will calculate the Norton's equivalent resistance. Now here, for that purpose, we will draw the circuit in which this load resistance should be replaced by the internal resistance, voltage source, and this voltage source will be replaced by the respective internal resistances. Remaining elements will be the same. Means here, the figure for the step number 2 will be something, step number 3 will be something like this. The first source is replaced by internal resistance. This is 2 ohm as it is. Here is 1 ohm as it is. This is 6 ohm as it is. 2 ohm. This is 5 ohm. And here will be the A and B terminals. Here it is 2 ohm, 5 ohm, 6 ohm. Here this battery is replaced by the internal resistance, and voltage source has the internal resistance of 0. That's why it is replaced by the 0 resistance. And then we have 1 ohm again, and the last resistance is it of 2 ohm. Now here, if we are simplifying further, the two resistances are in series combination, means figure will be something like this. This is the figure. There is the A and this will be the B terminal. 5 ohm, 2 ohm, 6 ohm, and these two are in series, that is 2 plus 1 which is 3 ohm. This is 3. This is 3. Now, these two resistances are in parallel combination. I will use this portion. Two are in parallel combination. The two resistances are replaced by the single resistance having its parallel combination. Means final figure is something like this. Here is A, this is V. Here is Rn, which is in this direction. 2 ohm, 5 ohm, and it is the parallel combination Rp. This Rp is equal to 3 into 6 divided by 3 plus 6. 18 divided by 9, which is equal to 2 ohm. Now here, if we are finding the Rn, which is equal to 2 ohm plus this 2 ohm plus this 5. This is 2 plus 2 plus 5, which is equal to 9 ohm is the Norton's resistance. Now here, if we know the value of the IN and Rn, this is Rn, Norton's resistance. IN and Rn are known, then complicated network will be replaced by the Norton's equivalent network. And this network is known as Norton's equivalent network. This is Rn, and here this value is the IN, which is Norton's current. In our case, this IN is 3.03 amperes and this Rn is 9 ohm. Now, we can connect the load resistance which is removed in the first step. And in our case, the load resistance in this case is the 10 ohm. Now we can find out the current in the load resistance in this case, which is this IL is equal to total current, which is 3.03 into resistance of the opposite branch. In this branch current is known. In this branch we want to calculate the current, means the remaining branch is the opposite, which is 9 divided by resistance of the both branches, that is 10 plus 9, which is equal to, if we are simplifying it, we will get its answer, that is 9 into 3.03, which is equal to, here in this case 3.03 into 9, this value is 27.27 divided by 19, which is 1.43. This 1.43 amperes is the current flowing through the load resistance by using this method. Means this is the way to calculate current flowing through the load resistance by using the Norton's theorem. That's all for this particular video. Thank you.